Hey everyone, my name is Sophia Sharif. Welcome to my grade 11 functions project, The Math of the Krabby Patty Flip. Today we're going to be applying quadratic functions to an applied trajectory problem, even if that real world happens to be at the bottom of the ocean. So here's our scenario. Plankton has sent a 6-meter tall robot to crash the Krusty Krab and steal the secret formula. To stop him, SpongeBob uses his spatula to launch a Krabby Patty high over the robot, so Squidward can catch it in his order tray. The patty's height over time is modulated by the quadratic function h of t equals negative 5t squared plus 10 plus 1.5, where h is height in meters and t is time in seconds. To solve this scenario, we need to answer two key investigation questions. First, peak height and clearance. Does the patty actually reach enough altitude to clear Plankton's 6-meter tall robot? And second, total flight time. How many seconds does Squidward have to catch the patty before it hits the floor? To answer our first question about maximum height, we need to convert our standard form equation into vertex form by completing the square. First, we group the t terms and factor out our leading coefficient, negative 5. That gives us h of t equals negative 5, bracket t squared minus 2t plus 1.5. Next, we complete the square inside the brackets. We take our middle coefficient, negative 2, then divide it by 2 to get negative 1, and square it to get positive 1. To keep the expression balanced, we add and subtract 1 inside. Negative 5 bracket t squared minus 2t plus 1 minus 1 plus 1.5. Now, we bring negative 1 out of the brackets. Multiplying it by the negative 5 in the front turns it into positive 5 on the outside. Factoring our perfect squared trinomial gives us negative 5 t minus 1 to the power of 2, and combining 5 plus 1.5 gives us our completed vertex form, h of t equals negative 5 bracket t minus 1 squared plus 6.5. Reading directly from the vertex form, which is a bracket t minus h squared plus k, our vertex h, k is 1, 6.5. This means the Krabby Patty reaches its peak height of 6.5 meters exactly 1 second after SpongeBob launches it. Finally, we compare our peak height to the robot. Since 6.5 meters is greater than 6.0, the patty successfully clears Plankton's robot by half a meter. Now, for our second question, how long does Squidward have to catch the patty before it hits the floor? To find the total flight time, we set our height, ht, equal to 0. Since our quadratic equation, 0 equals negative 5t to the power of 2 plus 10t plus 1.5 doesn't factor easily, we identify our coefficients, a equals negative 5, b equals 10, and c equals 1.5. Next, we plug a, b, and c directly into the quadratic formula. T equals negative b plus or minus the square root of b squared minus 4ac over 2a. Substituting our numbers gives us t equals negative 10 plus or minus the square root of 10 squared minus 4 times negative 5 times 1.5 over 2 times negative 5. Simplifying under the radical, 10 to the power of 2 is 100, and negative 4 times negative 5 times 1.5 gives positive 30. That leaves us with the square root of 130 in our discriminant. Calculating both the plus and minus options gives us two mathematical answers. T1 is approximately negative 0.1 seconds, and T2 is approximately 2.14 seconds. In real-world physics, time starts at launch t equals 0, so a negative time just doesn't make sense. We reject negative 0.14 seconds as an extraneous root. That leaves us with t equals 2.14 seconds, meaning Squidward has exactly 2.14 seconds to catch the patty before it hits the ground. For our independent variable, time t, the mathematical domain is all real numbers, but our real-world domain is restricted to 0 to 2.14 seconds from launch until it hits the floor, since negative time is impossible. For our dependent variable, height h, the mathematical range is h less than or equal to 6.5 meters, but our real-world range is 0 to 6.5 meters, since the patty peaks at its vertex and can't fall below the floor. The solid red curve is our real trajectory, while the dashed purple line shows the rest of the mathematical parabola outside our domain. Starting on the left, our green launch point shows the patty leaving the spatula at 1.5 meters. It peaks at the purple vertex at 1 second at 6.5 meters, easily clearing our 6-meter obstacle line by half a meter. It comes back down to land on the floor at the orange landing point at 2.14 seconds. Finally, the blue rejected route at negative 0.14 seconds is dotted because the negative time isn't physically possible. To sum it up, this table outlines our 4 key features side by side: our launch height at 1.5 meters, peak height at 6.5 meters, landing time at 2.14 seconds, and our rejected negative root. Every value here directly matches our graph. Starting with Patrick, a common mistake when solving this quadratic model is including negative time, t equals negative 0.14 seconds. In the real-world domain, even though it's a valid mathematical 0 for the complete parabola, time cannot run backwards before SpongeBob launches the patty, so it must be rejected. Next, Squidward checks our reasonableness using symmetry around t equals 1 second. Both 0 seconds and 2 seconds yield a height of 1.5 meters, confirming our math. Finally, SpongeBob brings it back to the story's context. The vertex at 1.0 second and 6.5 meters represents the exact moment the patty reaches its maximum altitude, giving it the clearance needed to pass the obstacle before dropping back down and hitting the Krusty Krab floor at exactly 2.14 seconds. In conclusion, SpongeBob Patty clears the 6-meter obstacle, peaking at 6.5 meters and landing at 2.14 seconds. The main takeaway is that real-world domain and range must be bounded by physical limits from launch to floor landing. Thank you, order up, and let me know if you have any questions.